function like this K. And there are many kernel functions available in the literature that can be used to solve it directly. Okay. So now I can start with another a very relevant advanced SVM called twin support vector machine. So essentially it was developed in 2007 by the team of IIT Delhi, Jayadeva, Khemchandani and Suresh Chandra. So they have developed this algorithm uh, with the concept that rather than having uh, a single hyperplane, so we can have a two non-parallel hyperplanes. As if we compare with a conventional SVM, so essentially they propose called a twin SVM. This is a binary classifier that essentially determine two non-parallel hyperplanes by solving two SVM type problems, and each size is smaller than conventional support vector machine. So essentially, this twin support vector machine is in the spirit of proximal SVM. If you know the GPSVM, generalized eigenvalue proximal SVM. So, and what we see that it has been employed on several benchmark data sets. So this twin SVM is not only fast, but it shows better generalization ability. So, and it was proposed in 2007. And after that, it has been widely used by the researchers. So if you look at it, there are more than 1,000 papers on twin SVM with the same idea. So essentially what happens if you see that rather than having one large SVM formulation, so the twin SVM essentially have two smaller kind of SVM like 1 and 2. So this algorithm essentially find a two hyperplane, one for each class. You can see here, one for each class. So there are two hyperplane, and these hyperplane are essentially non-parallel hyperplanes. Okay, and they classify points according to which hyperplane a given point is closest to. So if I look at the first term in equation 1, so is nothing but the sum of square distances from the hyperplane to points of one class. Therefore, minimizing it tends to keep the hyperplane close to points of one class. For example, class plus 1. And the constraints essentially require the hyperplane to be a distance at least 1 from the points of other class. For example, class minus 1. And a set of error variable is used to measure the error wherever the hyperplane is closer than this minimum distance of 1. So essentially, the second term of the objective function, it minimizes the sum of error variable, and thus it attempts to minimize misclassification due to points belonging to another class. So if I see in a more general way that here twin support vector machine or TSVM, it comprises a pair of quadratic programming problems like equation 1 and equation 2. So in each QPP, the objective function corresponds to a particular class, and the constraints are determined by the pattern of other class. So essentially, the twin support vector machine, it give rise to a two smaller size quadratic programming problem. And if I look at its computational complexity, since it is solving to a smaller size of SVM, so each size is, for example, 50-50%. So the ratio, if I just calculate the runtime, it is approximately 4 times faster than standard SVM, if you look at it. So when we solve this problem, so the idea is same, that we just first construct the Lagrangian function L, take the partial order derivative, and then we solve it, and we can get 3 and 4. And then we can calculate parameters W and B in this manner. But what we observe that in 3 and 4, equation 3 and 4, the invertibility issues are there. So H transpose H, G transpose G, they are square matrices, but all square matrices are not invertible. So to handle that issue, so we have manually added this delta to make the matrices invertible. So this is one of the constraints in twin SVM, but it has been resolved by the researchers after that. So now this is another very efficient algorithm was developed in 2009 that so what they did, so essentially if you look at the twin SVM formulation, the two major change, one is they replace inequality with the equality of the constraints, and they replace with the one norm of the slack variable with the two norm of the slack variable. Okay, and the third is that since it's a two norm of slack variables, so the imposition of non-negativity restrictions has been removed now. So due to reformulation called least square twin SVM, this is extremely fast, and we are simply solving system of linear equations, and since we are able to directly solve it, we do not need any kind of optimization toolbox. So now I'm moving forward to discuss another very interesting algorithm called improved twin SVM. So what they're doing, they reformulate this problem to make it feasible for the larger scale data. How? So, and then further they minimize the structural risk that results in improved performance, and it avoids the computation of the matrix inverses, while as other given baseline models need to calculate the matrix inverse, which is infeasible for larger scale data. And ITSVM, that it doesn't deal to the kernel generated surfaces, unlike we have seen the baseline algorithm. Okay. So if you look at this problem, that it something looks like twin SVM, except the first term. Okay, and unlike first term of each objective function, and the second as they are considering this one as a equality constraints in the problem. So due to that, they are considering it as a constraint. So if we just writing its Lagrangian function, and we are writing it as a constraint, and we are solving it. So when we solve this problem, what we see that we can see the beauty of this algorithm in 21, and that we have this dual formulation, and we have this Q tilde, and Q tilde we can see that this is free from the inverse. So in the baseline algorithm, what we see that invertibility was there, even though matrices were not invertible. So people have developed a number of algorithms to address those issues. But in this algorithm, what we see that we even do not need to calculate the inverse of the matrices, right? And the second is, if we look at the formulation, so we are just imposing the kernel directly, means in place of A, we are simply writing phi A. But in the case of twin, you will not find like that. You see that. Okay. So okay, so we are able to see that we are able to find out the matrix solution, and the matrix appear is free from the inverse for both the cases. Okay, and finally we can calculate it and we can solve it similar to TNSVM. Now I'm going to discuss another very efficient algorithm called large scale pinball twin support vector machine. What it does. So in order to make the model's formulation suitable for larger scale data, we reformulate our problem in such a manner that it merits both the twin bounded SVM and pin GT SVM, except the calculation of the large scale, large matrix. So, and the second is that these changes are the introduction of regularization term, as we have seen in TBSPM, and we also added an equality constraint. Since we are using the concept of pinball loss, so due to that, our proposed idea is sensitive to noise and more stable for resampling. And in this problem also, we are handling the problem in such a way that we are avoiding the invertibility issues in the formulation. So it means that it is applicable for the larger scale data. And it also handle the kernel trick directly in the problem. However, if we look at the baseline algorithms of tune SVMs, so they are dealing with the kernel generated surfaces. And the last is that it possesses structural risk minimization principle, unlike the baseline algorithm. So it improves the performance of the algorithms. So more details are available. So what I'm presenting here, you can find out from this paper, Machine Learning, published in 2022. So this is the formulation that we have the equality constraints and we are imposing here pinball loss functions. So if you look at the second constraints here, inequality constraints here. So if tau goes towards 0 here, so essentially this last constraint of both the problem is reduces to xi I greater than or equal to 0. So they are essentially same as twin bounded SVM. So twin bounded SVM will be the particular case of this algorithm. And we are using this pinball loss function in such a way that we are giving penalty to positive to all data points. So when we solve the problem, I think I'll try to skip this one as it is straightforward that we construct the Lagrangian functions, take the partial order derivative, and then we solve it, and we are getting this 37 and 38. And in 37 and 38, if we look at the matrix Q tilde is free from the inverse matrices, both. So once we got the solutions, then we can find out the hyperplane corresponding to each class, and the decision function is similar to the previous baseline algorithm like PIN-GTSVM. And when we do for the nonlinear case, so for the nonlinear case, as I mentioned that we are directly incorporating kernel trick, like replace A with phi A, B with phi B. So by doing that, we go exactly on the similar fashion, and we can get the formulation in the same way, like 43 and 44, and you can see the Q tilde is also of similar kind of. Okay. Okay, let me discuss a few numerical experiments here. So for we used NDC data sets, and these are the details of the NDC data set, that training and testing size, number of features. So when we employ the baseline algorithm, the first three columns, TBSVM, TWSVM, and PNGTSVM, so they are working fine, but when the size becoming large, so they are going out of memory when we implement on the same system, same computational machine. However, the last algorithm, that is our proposed idea, is performing very well on the larger scale data. Okay. And then we also have done for the smaller size data, just to show that whether results are significant or not. So, and we observe that our algorithm is not only works for the smaller, large data, but also works for the smaller size data. Okay, so I'll discuss one more formulation here. A large scale fuzzy least square tweeness beam for class imbalance learning. We are using the concept of fuzzy membership. We developed one concept especially to handle the class imbalance data sets. So just a motivation that we analyzing the existing algorithm, there are several shortcomings. First is the baseline algorithm involve matrix inversion that act hindrance in applying to other large data sets. And both algorithms implement the empirical risk and assume that the matrices appearing in the formulation are always well conditioned. However, in real world problems, this assumption may not be well satisfied and hence lead to lower performance. And both the formulations solve linear and non-linear separately, as non-linear case is different from linear case when linear kernel is used. So, and what are the contributions and what are the advantages of this algorithm? So, more detail can be found here. So, what we not here we'll see. So, the advantages here that first we reformulate the primal of this paper in such a way that it is suitable for the larger scale data. It also minimizes structural risk minimization principle to improve the generalization performance, and it's also avoid the invertibility issues in the formulation. And next is also incorporate kernel trick directly. And finally, which is very important, that it handles the class imbalance problem. So this work appears recently in IEEE transactions on fuzzy systems. So if you're interested, please go through this one. So, and this is the original formulation of this paper, large scale fuzzy least square tweeness VM. So essentially, if you look at it here, S1 and S2, they are the fuzzy membership weights. So we are giving appropriate fuzzy membership values to all data points. So, and how to do that? So you can see that for a positive class data point, we just say this is 1. And for another data points, we are just using this membership functions. Okay. Now, if we look at the formulation that this formulation 45 and 46. So how to solve it? First, we construct a Lagrangian functions, take the partial derivative and calculate the dual. Okay. So this is the Lagrangian functions, and we just take the derivative, use KKT conditions, and finally we are getting this W1 B1 and W2 B2. So W1 B1, you can see that it also free from the inverse of the matrices. Okay, and we can find out this unconstrained minimization problem with Q tilde, which is also free from the inverse matrices. And we are using this SMO techniques here to solve this problem. So because SMO algorithm works very well and easy to use. So for more details, please see this paper, Kirti and Shevde. They developed this idea for least square SVM. So we incorporate the same uh, algorithm for our proposed idea because it is relevant, and we reformulate in the same manner, and then we use it, right? We have written a general formulation in for our problem. Okay, so you can see that this is the SMO algorithm for this one. Now, just to see a few applications. So first is we are using Alzheimer disease algorithm, Alzheimer disease data sets. We have used ADNI data sets. So ADNI datasets is publicly available. You can see, you can find out this ADNI website. It is mentioned here. You can easily download. So there are few steps to do that. If you go through that, so you can easily find out. So the main aim is to evaluate the Alzheimer's disease via neuroimaging approaches. I'm sure that some of you are aware about Alzheimer's disease. So Alzheimer's disease is essentially a progressive neurodegenerative brain disorder disease, and it was first it came after the name German doctor Alois Alzheimer, who was the first to diagnose this disease in 1906. And it is characterized by accumulation of amyloids, plaque, and neurofibrillary tangles in the brain. And this disease is mostly common for people having age more than 65. And due to this, it causes cell damage in the brain and death in critical brain areas that impact memory and cognitive functions. According to the World Alzheimer report, it shows that around 50 million people are affected by this disease in 2018, and it may go 3 times, that is 150 million people in 2050. So this is really alarming, and we need to work and we need to find a solution. So far, as such, no cure of this disease, but we have the solution in such a way that if we are able to detect this disease at the early stage, so it can be stopped at that level. So this disease started at the age of 30 or 35, but we came to know after 65 or 60-year age. Then very difficult to cure that time. So early detection is the important research problem these days. So there are several symptoms that affect the cognitive functions, like challenge in planning and solving problems, confusing day from nights, inappropriate behavior, inappropriate use of words, mood changes, memory loss, and gradual loss of ability to perform simple tasks, and loss of vision, and inability to recognize and use familiar objects. So we apply this algorithm on this ADNI data sets, and we see that uh, our algorithm has an accuracy or average rank or overall win-tie loss is performing well than these baseline algorithm, but again accuracy is very low, that is 0.68%. So we need to work a lot. And if you see the comparison with the time, so our algorithm is also efficient in terms of time. So those interested to work in twin support vector machine, please see this paper published in 2022 named Comprehensive Review on Twin Support Vector Machine. This is the updated survey. So interested researchers are welcome to read this paper. So you can see that a lot of work has been done in different variants of this algorithms, and it has been applied in several directions like Alzheimer's disease, breast cancer, human activity recognition, text categorization, EEG signal classification, image denoising, entries in detection, speaker recognition, and several other diseases. And I'd like to just highlight one more work that is deep learning for brain age estimation. So if you are interested to work on brain age is also one of the most important issues that suppose our age is 30, but our brain age is 50, and but we are not aware. Okay, so we need to know. So this paper could be helpful to understand, see, and what are the future issues in this directions. So in this work, we essentially characterize brain age estimation models based on the deep learning architectures, and we classify these architectures based on slice-based or voxel-based input data, and we examine the modality, size of the data, performance, and data sets used. And we further enumerate several key challenges and directions that can be explored further. Some of the directions here, like explainability in deep learning for brain age estimation, integration of multimodal data, and brain age difference with cognitive decline, and computational complexity, significant brain region extraction, and developing a deep learning architectures that can help to improve the performance to predict the brain age, and adversarial perturbation and uncertainty estimation. So these are the possible directions. And if you're interested to see our projects, so we are working specifically for the classification predictions of Alzheimer's disease, and we are developing shallow and machine learning algorithms for several tasks. So, and interested research are welcome to contact us, and thanks to the funding agencies to support our research. And with this, I can thank again for listening my talk. So I can take a few questions now, if any.
Thank you. Thank you, Mr. M. Tanvir, sir, for giving us the details knowledge about linear and non-linear SVM and several algorithms like twine support vector machine, improved twine support vector machine, large scale pinball twine support vector machine and their functions. And we have come to know about Alzheimer's disease in details and its symptoms and the results of evolutions of these SVM algorithms specifically for Alzheimer's disease and many more medical data. So I hope all the participants and dignitaries here have accumulated some details about different SVMs and their solutions in larger scale from Dr. M. Tanvir, sir. So you can ask any question if you have. Sir is with us. Or you can drop your question in the comment box section or chat box section of Google Meet and YouTube. Participants, you have any question? Okay, I think sir have given us details knowledge about SVMs in so depth that participants have no question. So thank you, sir, for spreading your valuable knowledge and expertise among us. And I'm sure that it will enrich us in future and help in grow in our respective fields. So, sir, a certificate for you as a short token of appreciation from our side on behalf of Global Institute of Science and Technology for spending your valuable time with us today. So this is the certificate, sir. You can see on screen.
Okay, thank you, madam.
Thank you so much, sir. Participants, the attendance link for this session is given in the Google Meet chat box as well as in the YouTube comment section. Please check out there. And we have another session today from 2:30 p.m. And today we will have Professor Dr. Vishwapati Jana sir from Vidyasagar University in our second session. So all the participants are requested to join on time, please. So
Ma'am,
once again,
when will be the exam today?
after the second session.
Thank you.
Thank you. So all the participants, thank you, and
Yes,
sir, thank you so
ma'am,
much.
ma'am, I've got a question. Is the
Oh,
test
okay.
going to be held? Is the test going to be held now or after the 2 p.m. session?
After the 2:30 p.m., sir. The time is 2:30. So after the 2:30 p.m. session.
After the 2:30 p.m. session.
Yes, sir.
Oh, okay. Because it has been written in the WhatsApp group that we have to finish the test by 11:59. So is that
It,
It is
yes,
11:59 p.m. No,
yes, yes, yes,
is that
that is
11
before
p.m.?
the end of today, right?
yes. End of today, yeah.
Okay, I'll see. Thank
Okay.
you, ma'am.
Thank you, sir. Once again, thank you, Mr. M. Tanvir, sir, Dr. M. Tanvir, sir. And
Thanks,
thank you, all
madam.
the participants. Thank you, sir.
I'm
This is the
closing now.
end. Yes, sir. Yes, sir.